Alright, let's work some polarization problems. Alright, first, linear polarizers. Imagine sunlight, which is unpolarized, passes through three ideal linear polarizers. Ideal meaning they absorb one polarization and pass the other with, perfectly absorb one and perfectly transmit the other. The first polarizer passes horizontally polarized light. The second one passes light polarized at an angle of 20 degrees from the horizontal. And the last one passes light polarized at 35 degrees from horizontal, rotated in the same direction as the second polarizer. If the intensity of the sunlight before passing through the polarizers is 1 kilowatt per meter, what is the intensity of light after passing through them? Okay, so what do we got? We start with sunlight, which is polarized all different directions. It's doing all kinds of random stuff. And that light is going to go then into a polarizer that passes horizontally polarized light. Then we're going to take the light that comes out of there and we're going to send it into another polarizer, but we've rotated this one so it passes light polarized at 20 degrees relative to the horizontal. And then we have another one which is rotated in the same direction as the second one, but it's rotated such that it passes light at 35 degrees. I have not drawn those angles very accurately, but you get the idea. And then we want to know what comes out. Well, after going through the first polarizer, right, if we start off with some intensity of light I0, which is 1 kilowatt per square meter, after going through our first polarizer, right, unpolarized light going through an ideal linear polarizer, I'm going to get half of it through. All right? Then when I go through this polarizer, I'm going to start with this, and I'm going to multiply it by the fraction that gets through. The fraction that gets through is just cosine of the angle squared. So what I'm going to get right here after coming through this one is just going to be 1/2 I0, what I started with, times cosine of 20 degrees squared. Right? Remember, it's squared because we're talking about intensity, not the amplitude of the electric field. All right? Now when I go through this last one, my light coming out of here is at 20 degrees from the horizontal. So the axis that is passed here is at 35, which is 15 past 20 degrees, right? We said this one's rotated from the horizontal in the same direction, but it's rotated more. So the angle between our polarization and what polarization gets passed is from 20 to 35, that's 15 degrees. So over here, I'm going to have what I started with before that polarizer. And then I'm going to multiply by the fraction which gets through, which is the cosine of 15 degrees squared. So there you have it. All right, so I just need to plug in my numbers. First of all, so let's call this is what I get out right there. First of all, looking at it, it's got the right units. It's got units of intensity. These have no units. Yeah, and it seems reasonable, right? I'm reducing by each factor each time. Looks like a simple problem. Hopefully I did this right. Let's plug the numbers in now. So plugging the numbers in, all right, I have half times my initial intensity was 1 kilowatt per square meter. I'm not going to do this in SI units. I'm going to leave it as kilowatts because there's no other units in the problem. And my answer will just be in kilowatts per square meter. Then I have to multiply by the cosine of, put parentheses here to make sure I don't make any mistakes. Cosine of 20 degrees, Python likes me to put angles in radians, so let's convert that to radians by multiplying by pi, dividing by 180, and then I have to square that. And then I'm going to multiply by cosine of 15 degrees. And square that. And 0.412. So my answer is 0.412 kilowatts per meter squared. There's my answer. All right. Now, next problem. Brewster's angle. A flashlight produces unpolarized light. If I shine the flashlight onto a glass, plate. If the glass has an index of refraction of 1.47, at what angle relative to the normal should I shine the light onto the glass to produce a reflected beam which is completely polarized? Okay, what's the physics going on here? I shine my beam into the glass, some of it's reflected, some of it's transmitted, right? If I shine my light right in at Brewster's angle, well, if I look at this polarization, some of that transmits and some of it reflects. But if I look at this polarization, all of that transmits if I'm at Brewster's angle. So whatever reflects will be linearly polarized. Send in unpolarized light, I get out light, which is linearly polarized, because I can think of my unpolarized light at any moment in time as a sum of these two polarization components with different amplitudes and different phases. But the one transmits 100%, so I only get the other one. All right, so really what I need to find is Brewster's angle. There's an equation in your book, probably in your notes, it was in the video, for Brewster's angle. But as you've probably found out, I despise going right to equations. I'd rather learn physics than learn equations. So let's pretend I don't know that equation, and let's think about the physics that's happening. And let's review Brewster's angle. So at Brewster's angle, what we said is I send in a beam and it reflects, right? Some of the light transmits, all right? And we said that this polarization, if I have my medium, kind of the electrons in there wiggling back and forth like this, if this beam is at 90 degrees to the way that's traveling, you can't emit in that direction, right? So you'll get no reflected beam. So what we want is we want the angle between the reflected beam and the refracted beam to be 90 degrees. All right, so let's set up this problem. I'm going to call this angle right here. Well, this angle right here, we want it to be theta Brewster, right? Which means law of reflection says this is theta Brewster. And I'll call this theta 2, all right? So what we want is theta Brewster plus 90 degrees plus theta 2. After we've gone all the way down there, we've rotated by 180 degrees, right? That's what we want to be true. But we've got one equation, two unknowns. We want to find this, but we don't know theta 2. Well, how do we find theta 2 in terms of theta Brewster? We use Snell's law, right? We're refracting. So Snell's law tells me n1 sine theta 1, which in this case is theta Brewster, is equal to n2 sine theta 2. All right? So I can get rid of theta 2 in this equation by solving this one, right? Theta 2 is just going to be 180 minus 90 minus theta Brewster. So 90 degrees minus theta Brewster. So this is just n2 sine 90 degrees minus theta Brewster. But the sine of 90 degrees minus something is just cosine of something, right? So this is just n2 cosine theta Brewster. If I divide both sides by the cosine, I'm going to get n1. Sine divided by cosine is tangent theta Brewster, and that's equal to n2. So that means the tangent of theta Brewster is n2 over n1. So theta Brewster, what I want is just the arctangent of n2 over n1, but n2, that's just the glass, right? That's 1.47. That was given in the problem. n1, that's air, so that's about equal to 1. And now I can just go to Python and take the arctangent of 1.47 divided by 1. Now Python gives that to me in radians. If I'd rather have it in degrees, I'll just multiply by 180 degrees per pi radians. And that's 55.8. So 55.8 degrees. And we're done!